Let's talk about Markov chains. Markov chains is named after a Russian mathematician by the name of Andrei Markov. Had a big bushy mustache and a beard. Anyway, but it's basically lots of probability, and it has to do with matrices and this thing called vertex edge graphs that you have not learned before, but that's okay. It's actually going to be really easy if we take it one step at a time. Really cool thing here. So we're going to have just a very simple game to get this idea going, and it's this. We're going to roll a six-sided die. Die is plural, singular for dice. And if you roll a 6, you lose. If you don't, you're still in the game. So you could do this thing where like a bunch of people are rolling dice and the person that lasts the longest. It's really basic, but the more basic the game, the better the example is in order for us to start with an example like this. So you can't see what I'm rolling, but here goes. So 0 rounds have passed so far, and I just rolled a 5, so I'm still in the game after one roll. So I rolled a 6. Ah, man, I lost on the second one. So you can do this if you want. I'm not. Let's move on. So the very first thing says, draw a vertex edge graph. So there's our first item of business. So number 1 was a vertex edge graph, and that is some vocabulary that you have not encountered before. But that's okay. This is going to be really simple. In this game, you're either in or you're out. You either rolled a 6 or you didn't. Okay, so a bunch of people sitting around and they're all rolling dice, and the person that lasts the longest wins, and you have to all roll at the same time. It's that kind of thing. So what we need to do is think about what could possibly happen, and you could stay in the game or you could be out of the game. And what I like to use, the word I like to use is what states could you be in. I don't mean state like Virginia or North Carolina or whatever. Actually, Virginia is a commonwealth, but whatever. I'm referring to, sorry, off topic. I'm referring to what are the things that could happen in this game. I could be in the game, I could be out of the game. I could be winning or losing. So I'm gonna just make it two separate things. So I'm in the game. I have a squeaky marker, and I have another one that says I'm out. Out of the game. Okay, so all we've done so far is just identify, this blue marker's not working too well. I've identified a marker that doesn't work well, and I've identified the different things that can happen in this game, okay? So now we're gonna delve into probability, which is what we dealt with in a previous lesson. So if I roll this die right here, and I wanna stay in the game, then I'm gonna move from being in the game to staying in the game. So what I'm doing is I'm drawing an arrow from this bubble to itself. And the probability of that happening is, okay, and I don't mean to oversimplify things here, but you have a 1, 2, 3, there's a good marker, 4, 5, or 6. And if I'm gonna stay in the game, then I'm gonna roll a 1, 2, 3, 4, or 5 out of 6. So to stay in the game, there is a 5 out of 6 chance I stay in the game. This is building the vertex edge graph, okay? Now we're gonna see what happens if I go from being in the game to being out of the game. So let's draw an arrow from here to here. So I'm moving from one state to the other. I'm moving from one possibility to the other. I could stay in the game or I could be out of the game. Well, if I'm gonna be out of the game, then I rolled a 6. There's a 1 out of 6 chance that'll happen. Let's use the good green marker. There's a 1 out of 6 chance that'll happen, okay? Now let's delve into this over here. We're delving into the probabilities of other things. So if I'm out of the game, the probability that I stay out of the game, I'm going from being out of the game to staying out of the game. Well, that's 100%. Like when you're out, right? There, nowhere in these very simple rules, nowhere in the rules did it say you can get back in. No, you're out. That's it. You rolled a 6, you're out. Sorry. So there is a 100% chance that when you're out of the game, you're out of the game. I'm not going to say it's 100. I'm going to say it's 1. We're using fractions. This is like 1 out of 1. And if I'm out of the game, there is a, whoa, this should be green to match everything else. There we go. So 1 right there. It's starting to look like an ear on the side. If I'm out of the game, I'm not coming back in the game. So there's a 0% chance that I'm coming back in the game. So Going from out of the game to in the game is a 0. Let's review just a little bit really quickly. If you're in the game, 5 out of 6 times you're staying in the game. 1 out of 6 you're out. If you're out of the game, 100% of the time you're out of the game. You 0, never come back in. All right? That actually answered the vertex edge graph. Now we're going to do this thing called an adjacency matrix. Adjacency matrix. What in the world is that? Okay, we have 2 things that could happen. You could be in, you could be out. 2 states in this. So let's grab the good green pen. Let's actually not. Let's use this purple pen right here. Purple marker. I'm going to be writing a matrix. I'm going to call it A, by the way, because they said so. So this is going to be like capital A equals, so here we go. Capital A equals the 2 things that could happen. I could be in or I could be out. Let's not make this harder than it is. And I'm going to have 2 rows in my matrix, and I'm going to have 2 columns, and they're the same. In and out. I'm in the game, I'm out of the game. And all I need to do is look at my little vertex edge graph. Let's not be deceived by the word graph. I know it's not a graph in a traditional sense. It's just a representation of what's going on. But what I'm going to do is take the numbers that lead from one to the other and put them in the right place. So this is where I start. This is where I end. So from here to here. Let's go slowly. If I'm going to start in the game and finish that turn in the game, I start here and I go back to being in the game. If I'm going to be in the game and stay in the game, that's a 5 out of 6 chance. Whoops. 5 out of 6. There we go. 5 out of 6. All right. If I start in the game, but then I move to being out of the game, I roll the 6, right? And there's a 1 out of 6 chance that would happen where I start in and I go out. So in to out, that's 1 out of 6. Okay? If I start out of the game, if everybody else is still playing, I'm out, there's a 0% chance I come back in. So going from out to in is 0. Start here, end here. Going from out to out is a 1. Okay, there's our adjacency matrix. What does it mean? Well, it didn't ask what it meant, but here's what it means. This is the probability of you being in any particular place at the end of, watch this, 1 turn. Cool. So here we go. Number 3, find A squared. So number 3 is find A squared. So we're going to find out what A squared is. And when we do, that's going to tell us, well, the probability that you're going to be in the game at the end of 2 turns. So let's do it. Now, I know there's not a laptop in front of me right now where we could go to desmos.com/matrix and type this in. I'm actually going to use a graphing calculator, but here's what you should do on these problems. You go to desmos.com/matrix, you type in A, and then when you need to find A squared, don't make it hard on yourself. You just do A to the 2nd power, and it'll crank it out for you. So here goes. We're going to find A squared. We're going to have in, we're going to have out. There we go. In, out. And I'm going to grab a calculator. And we're going to do this very quickly. And while I'm doing this, you may want to go ahead and write the sentence that I'm about to write. The sentence I'm going to write is the answer to the question, what does it represent? Well, I'll tell you what it represents. It represents the, hope you're writing this down, the probability of being in any particular state of the game after 2 turns. I'll say that again in a minute. Okay, I turned my answer into a fraction. I could use decimals if I wanted to. Actually, I think I will use decimals. I'm going to round to 2 decimal places. So let's not use fractions. Let's use decimals. So 0.69, 0.31, 0, and 1. Okay, and again, what does it represent? I told you the sentence. I probably will not write it word for word, but this is the probability of being in any state of the game at the end of 2 turns. in the end of 2 turns, 2 rolls of the die. So let me actually slide this over just a little bit so you can see it. There you go. All right. The end of 2 turns. There it is. Adjusting the camera so you can see everything. That's an ugly 0.31, but that is a 0.3. And so if I said, okay, I start this game. I'm in the game, right? What's the probability that at the end of 2 turns, I'm out? I started in the game. Like, hey, I'm playing. I grab my die. And at the end of 2 turns, you got to watch where I'm pointing. I'm in the game. At the end of 2 turns, the probability that I'm out is 0.31. Let's call it what it is. That's 31%. So 31% of the time, I'm out of the game at the end of 2 turns, assuming I'm rolling a fair die. Okay? If I want to say, all right, I'm in the game. Cool. We're in. We're playing. At the end of 2 turns, what's the probability that I'm still in the game? I start in the game, I'm still in the game, 69%. Okay? So then the next one says, find a cubed. What does it represent? So here's number 4. A cubed. And so we're going to find it. I'm going to squeeze it in down here, and we're going to have even crazier decimals. And I'm using my calculator. You can use desmos.com/matrix. And so here it is. Actually, let's just go ahead and write down a cubed equals, you can only see my head right there, can't you? In, out, 0.57. Oh, nope, let's make that 0.58. I'm going to use 2 decimal places. And 0.42. 1, there we go. In, out. All right. So here it goes. What does it represent? I am running out of space, so I'm not going to write the same sentence, but the sentence is this. It's the probability of being in any particular state of the game at the end of 3 turns. All right, once again, man walks up to you and he says, I want to play this game. All right, you're in. 3 turns later, there's a 58% chance he's still in, 42% chance he's out. Okay, so let's answer number 5 and number 6. Here's number 5. Number 5 says, what's the probability you will lose the game within 3 turns? So lose within 3 turns. Now you might have lost at the end of the first turn or second turn or third turn, but at the end of 3 turns, you're out. So lose within 3 turns. Okay, let me point. This is important. If I want to know the probability that I lose within 3 turns, I'm dealing with this guy right here. If this would have said 2, I'd be dealing with a squared. If I would have said 1, I'd be dealing with a to the first. Really important. All right? That's where exponents come in handy. The probability that I lose within 3 turns, I was in the game, now I'm out, 0.42. So losing meaning you're out of the game. So 42%. All right, number 6, here we go. Probability that I'm still in the game after your 3rd turn. So in, within, let's say after. In the game after 3 turns. All right, stating the obvious again. 3 turns, I better be using this one. I was in the game. This is the beginning. This is the end. I started in, now I'm still in, 58%. By the way, let me state some other things here too. We never start out of the game because, you know, that's like, hey, do you want to play? No. Well, then you're never going to get back in the game. 0% chance, and there's a 100% chance you're still out. So those are kind of awkward questions to even ask in the first place.